All right, we're back. Now we want to talk about St. Venant's principle, and we're going to actually do a few of these in the geometry of things. See, we started out with forces, now we're going to do geometries. And St. Venant, this guy here, Berry de St. Venant, 1797 to 1886, was an applied mathematician. And back in those days, the dudes were really like focused on, oh, math, 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 math. But of what real things can we do math on? And they were trying to figure out back then, what are the equations for how things bend? And he did a very famous experiment because, you see, him and his friends were like, oh, let's figure out how things bend. And let's see, we've got a wall and a beam sticking out from the wall, and then we're going to apply a force to the end, and we want to figure out when this thing breaks. Okay, when you apply this force, it takes a lot of force to break this beam. Let's see, the force starts to cause stress fields in the tip of the beam, and you had a whole bunch of PhD theses and stuff going down right here. Meanwhile, the beam was trying to break here. So Berry, the dude, said, you know, if you are a long way away from where the action is, you can forget about what's happening here and just focus on the action. In other words, what is a long way? Well, if this is D, and this is L, if L is a lot greater than D, and that means like, 3 to 5-ish, you can forget about what's happening here and focus back here. So the way you use this in design is, if I want to control something, I have to grab it by 3 to 5 characteristic dimensions. If I don't want to be controlled by it, I stay 3 to 5 characteristic dimensions away. So for example, remember that drawing I did earlier, that sketch on top of the picture where we showed here was a motor and had this long shaft extension to the gear and another gear. You either want this gear to be right up tight, if you're using the shaft of the motor, right up tight, or if way far away and then you put a bearing here, an outrigger bearing it's called. And that way, if this bearing is at least 5 of these diameters away from the motor, this bearing will not over-constrain or control this motor's bearings, and it won't wear them out. Your worst nightmare would be to have a motor with a shaft maybe like that, and the gear, and then a bearing here that maybe was, let's say, 2 to 3 diameters away from the bearings in the motor, because then this bearing would fight those bearings. So this is how, as a design person, you can start to lay out your machine thinking about where you're going to need your elements, and to be a good design person for that. And notice we have things like drawers. You ever have one of those old dressers that were made real cheap? And this is a really expensive drawer set here, and it's got ball bearing slides on it. And it's wide out, and it moves, rolls nice. And it's what's called a compound slide, notice. So you always have a long engagement length of bearings with respect to the width of the drawer. So it always slides nice and easy. As opposed to some of those dressers which have just wooden runners way on the outside of the drawer, and it works really nice, and it jams and it fights you. So let's get some feeling for St. Venant's principle, because remember, to be a good designer, you have to have the math and the thinking, but you want to wire your neurons to you want to be able to feel, and I understand, I can feel it. So let me ask my friend Lana here to come on up, and she and I like to do a lot of design work and stuff together, and I'm gonna do this I'm gonna control Lana because she likes it when I control her, right? So let me I'm gonna grab her and no, break away, get away. I was actually trying to hold her. Let's do that again. I can't control Lana. All right, you're so strong, you control me. Now, I'm going to be able to get away that way, can I? But she knows St. Venant's principle, so she knows what to do to control me. Yo! See? She's controlling me. Now look at this is one characteristic dimension, 1, 2, 3. She's got me by 3 characteristic dimensions she can control me. Thank you, Lana.
You're welcome.
See? It actually works. So if any guys out there like martial arts fanatics, when you practice your martial arts, you'll notice a huge chunk of it is actually applied St. Venant's principle, physics. It works. Let's go a little more deeply into it, on how we design bearings, how we figure out what's happening with bolts. When I'm designing any kind of support system with bearings, with bolts, with wheels, I'm never going to want to do something like this, where here is a shaft, and here is a wheel on the shaft, ground, and I've got some bearing here, and back here, motor driving it. Because what happens here is this shaft is going to bend a lot. The wheel, which is more than 3 characteristic dimensions away from the resistance to the force from the wheel will now dominate the bearing and wreck the design. I'm going to move these bearings close to the wheel. Now, a lot of y'all may be wondering how I can afford such a fancy wardrobe. Well, in reality, my wife makes all my shirts. She designs them, dresses me up nicely. But that said, how do I really afford all these fancy fabrics that she uses? She knows St. Venant's principle. And how does it apply here? It does, yes. What am I going to draw next? Think ahead. Think ahead to what's happening. Where does this come from? Here's the wheel, the shaft. And how do I know where to put the bearings? 3 to 5 away. And now extend this the other way. What if this was the gear? Remember that gear we were talking about? How many times have you seen a design that looks like this? So that's what's proper. How many times have you seen somebody do something like this? A motor and a motor shaft that sticks out. And then here's gear teeth. And they'll put a set screw, which is another nasty thing we'll get to a little bit later here. And here's the gear teeth. And they're doing this design for something like gear on a motor and then a bigger gear the motor drives. Here's the little teeth. What did we just learn about St. Venant? And what is silly about this? Doon 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 doon. Ding. Answer is survey says bad. Why? Because the forces from the gear teeth come through here. Here's your diameter D. And here's the bearings in the motor. And the forces from the gear teeth, because remember we just did about torques? There's a force, action and reaction. Here we are using Newton again. Whoa, as the gear teeth turn. So there's that tooth from the torque. The tooth force turns into a torque through the gear, through the center of the shaft. That means there's a reactive force through the shaft trying to bend the shaft, applied at about 3 shaft diameters away. And this force from the gears will now dominate the bearings in the motor, and it'll wear it out. So you have the, look at this clever, cool design. Oh, it works so wonderful, marvelous. And it works for 5 minutes, fantastic. Then 2 weeks later, dink, your motor breaks off. Oh, bummer, man. Well, that's just the detail. But that's what it takes to actually make a product and make money so you can afford nice fabrics, is getting the details right. What should you do here? Yes, no, you can't just call Ghostbusters. You got to do something else about it. So what we're going to do is we're going to use the principle of reciprocity. And if you don't like sleeping on your back, turn over on your side or your stomach. We have a problem that the forces are controlling the bearings. Just the way I was attempting to control Lana earlier. And she flipped it around. She controlled me. So we're going to take our motor, and here's the motor shaft. And I've read a lot of the religious scriptures, and nowhere, even in the footnotes, does it say, thou shalt have thy hub close to thine motor. No, 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 no. It doesn't say that anywhere. That means it's totally cool to flip it around and put the hub on the outside, which, by the way, makes it a lot easier to get to. You're making it super simple. See how we're connecting back? All these fundamental principles keep coming up. Here's the attachment. Here's the gear tooth. The forces come through here. Here are the bearings and the motor. Oof! Look, the bearings and the motor are one diameter away from the force. The bearings now control the force. That's how you apply St. Vinay's principle. Let's look at it in detail, how you do this for if you're designing a drawer slide. The purple is the slide or the runner. And notice how it keeps getting shorter. And look where my force arrows are with respect to the center of the purple slider. Oh, he's looking ahead. I know what he's talking about. He's talking about the center of stiffness. Remember that long list of fundamental principles that you've already read ahead and learned about. And notice as this engagement length gets shorter, where it will tolerate a force being applied has to go closer and closer to the center of stiffness. In other words, you can take a slide that looks like this, and you can move it back and forth without jamming if you go exactly in the center. If you were to try to push off center, it would crash and burn. And you wrestle with your drawer. If you've got a slider or drawers that have nice long engagement length, you can push anywhere you want and it's not going to jam. Peanut butter, no jam. It's a very, very, very tasty, wonderful treat of design to remember about. St. Vinay's principle. It's one of the most powerful ones that you can learn about for laying out your machine. And notice we didn't have to do any math. How would you do the math for here? Well, later on when we have some of our modules where we're going to go through the spreadsheets that go through these different topics, we'll show you how you can actually calculate the amount of tilt or jam that happens. And being able to calculate how much it tilts based on the gap and the length. Whoa, we remember that. He was talking about that with respect to the joints for the new drill press thingy bopper he's going to be designing. Hey, wow, this stuff actually all works together. Yeah. You can actually model this very exactly to figure out how much clearance and length you want for what force. Look at this. There's actually spreadsheets that come with these modules that you can get also. And it goes through all these calculations. Next, the golden rectangle. Very important. I think you can get this from YouTube. Donald in Mathmagic Land. Download it, watch it, learn from it. Why? Because way back, right? Remember this dude, Pythagoras? Smart dude, what, 2,600 years ago, said, wow, you can find very interesting things in nature that look good that actually work really well too. And if you take a rectangle and you cut a square from it, and you get the same rectangle, the same proportions as the original rectangle, and it turns out those dimensions are about 1.6 to 1, that looks good. So when I'm laying out a design, and you can get golden spiral, all kinds of cool stuff out of this that you'll learn from Donald, that when I'm initially laying out a machine, what proportions do I do for things? And tying back into St. Venant's principle, we said if you want to control something, grab it by 3 to 5 characteristic dimensions. Can it be 2? Can it be 1? 1 is often pushing it unless you have really low friction. Turns out that spacing your bearings about 1.6 to 1 of a characteristic dimension if it's low friction is a good spacing for good motions. And when I'm laying out a machine looking at sizes of things and I'm not even sure exactly what things should be yet, sketching out things initially roughly, I'll pick those kind of dimensions. It gives me a good starting point from which later on my analysis is likely to show I'm in the neighborhood. Our next principle is Abbe's principle. Abbe's principle is sometimes called the Abbe error, or it's an error in measurement often called the parallax error. And let me demonstrate this here with my beam. And if you look right down here, right here, and I'm going to wiggle this because, you know, it's not exactly where it should be. So I'm here, and I wiggle a little bit. Hey, it's hardly moving. No problem. It's a great machine. Uh-oh. So watch what happens. And when I'm going to align that mark and this mark. And now I'm going to wiggle so I move 1 mark at the top. Boop. And now I'm going to make another mark down here. Huh, look at this. From here to here, what is that? I don't know. Let's measure and find out. We're using Jurassic units here we got 1 inch between the marks. And between these marks down here, we've got about 1/4 of an inch. This is my pivot point down here. And that's we're about 8 inches there and about 40 inches at the top. So from here to here was about 8 inches. And this is about 40. (40) divided by 8 is 5. 1 divided by 1/4 equals 4. They should be equal, but we're going to talk about that in a minute too. A very important thing in experimentation called the uncertainty. Very important part in engineering and science and machine design and life. But they're on the order of, and it tells us that, you know, it's not a factor of or square factor or cube factor. It's saying that an angular error is amplified by distance. Now, I want the camera to zoom in real close here and look what we did. So we came up with, yeah, there's about a relationship there. That's cool. We can use that philosophically. Now let's start to dig into the fine points just a little bit. Because remember, we're going to be thinking about quality and precision. Remember getting back to Occam's razor, the cost versus performance. Look where we were pivoting about. And if you really zoom in closely, where did I draw the mark? Let's look at what our uncertainties are. This is a very big part of what Dr. Abbe did for Dr. Zeiss when they were designing microscopes. And the history of this relationship is fascinating. Dr. Zeiss was a fantastically skilled design person, quality crafts person, but wasn't the most brilliant at math. And he kind of ran out of room for how good he could make his optics. He was polishing and polishing and getting better and better, the most brilliant polisher in the world, but his cost was going up and his performance wasn't going very well. Increase. He said, wow, I need a geek. So he hired Abbe, and Abbe came in and said, yo, dude, errors and parallax are amplified. So if you want to have better accuracy, applying Saint Venant's principle, you've got to have the proper number of characteristic dimensions with respect to what's the input and the output. and applied mathematics and the principles of uncertainty to find what is the problem. Once you find what the problem is by a careful search, you can then correct it. So now let's look at where we found our errors in here. Where could the errors be? Look what the first thing was. Go back and systematically trace. It's like the structural loop. I said the pivot is here. The pivot was actually down here on the ground. And yet I pivoted here and I took my measurements from here. The actual distances are 9 inches by, in terms of from where the pivot is, by 41. So in reality, first set of errors is 41 over 9 equals what? It's not 5. 9 times 4 is 36. Half of 9 gives me there, so it's around 4.5. Equals 1 over 1/4. Well, these numbers up here, I had earlier put up these marks with a tape measure, and right to the center of the purple is 1 inch. Look what I did down here. I marked by, and I want the camera to zoom in. I marked by putting, well, let me make it not move here. Let me start over. See the white space between the line and the beam? That's due to the thickness of the marker and the plastic encasement around the marker. This is a detective story. This is the cool thing about engineering. You find the errors, and they reveal to you, and you can have power over them. You can bring balance to your checkbook with good engineering. And that distance here is about like that. Well, let's measure that. About 1/8 of an inch. And I had that error on both sides. Is that right? Somewhere around there. So I'm not really a 1/4 inch of motion. I'm somewhere a little less than that. And if I go back and look at this more carefully, I'll see what I read, because I did my glasses on, as a 1/4 inch initially. Somewhere a little over a 1/4 inch. 1/4 inch is 0.25. So I've got some uncertainty with this measurement. I had some uncertainty with my length. And if I actually wanted to now really home in and prove Abbe's principle, quote, exactly, just 1 over 0.2, 0.22. And this now becomes, that went to 4.5. This is over 0.2, 0.22. This factor of 4 starts to inch up from 4 toward 4.5. Where, see, they're starting to get closer. This type of uncertainty analysis and digging into the details and finding all your sources of error is really, 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 A, it's fun. B, it's what differentiates the people who really get it right and can release a really great product that has high quality, no returns, and you capture the market and you do good stuff. Very, very important to get into the details. Okay? So remember, the big lessons here are angular errors are amplified by distance from the pivot point. When you're making measurements, you can identify first order things pretty carefully, but in a precision mechanism, a very high quality mechanism, there are uncertainties in how you do the measurement and how you do the design, and you have to dig in and finer and finer and finer details if you really want to not only initially make it simple, but make it accurate and reliable. Very, very important. Now, let's talk about how we would use this in design, for example. We just talked about the overall principle, but what if we were designing a machine? What are the implications of this? For example, I have drawn here a really big machine. And let's say I was trying to design a large gantry cutter. So I have, let's say I'm building a sawmill at home. Big bearing rails here. And I'm going to have some wheels like railroad wheels. If I draw this up, I'll have something like a piece of angled steel I'll lay down and a V-wheel shaft going through it. And over on the other side, am I going to put another angled bar with another V-wheel on it? And there's other designs we can do that are different than this, but we'll just pick this for now. As these roll back and forth, am I going to be able to put these so they're the exact distance apart? Or is there going to be some uncertainty in my design such that as I roll, they're going to spread apart? And how am I going to allow the wheels to do that? There's a lot of different strategies you can think about. I can let them slide back and forth. But if it's a very precision mechanism, that may not be so good because I have some slop in here. Can I do as this picture shows, and you're on page 312 here in the notes. One bearing is fixed to the table, and the other bearing has this little elastic hinge here. Because remember, if I have a distance h, and this is moving, as I move this carriage out, and this bearing wants to go over, this part here acts like a little pivot to accommodate the misalignment. Okay, so you can accommodate misalignments by building in these little pivot motions. How is this effect in measurement? Think about if you're measuring things with what's called a micrometer, where the measurement axis is right in line with the part you're measuring. Very accurate. Versus a dial caliper. Dial caliper, the bearings are on this level, and the measurement is way down at this level. So any bit of rocking in this head as it moves will cause an error, Abbe error. Now, look at the difference between this stylistic design here and this design. And what do you see? You'll notice that the thickness of this rail here to the length of this carriage is different than this length here to this thickness. This gets back to Saint Venant's principle. This particular slide is long with respect to the width, so even if there was some wobble, when I can't even feel any, but even if there was some error in here, it's a smaller angle which is amplified less by this length than if this was a really short carriage, and any wobble would be amplified a lot more because it's a bigger angle at the tips. So when you're designing a machine, you can start to think about back to the functional requirements for the machine. What does it require for me? Then you can use your analysis to say, here's the spacing between my bearings, and I'm going to make them a little wider spacing because I have the distance. So that way, because I know I'm going to have some error between, clearance distance between the bearing and the structure, it's going to make a smaller angle to give me less of an Abbe error at the action point of the machine. Okay? Very, very, very powerful tool. And my friend Dr. William Plummer at Polaroid many years ago designed a fantastically brilliant optical alignment system that used Abbe errors, the Abbe principle. That's what's going on here. And let's jump ahead a little bit to the structures chapter, because I know you've read ahead there. If I take a cantilever beam and I push on it with a force, at the tip here, I'll get some deflection, delta, but it's also going to have an angle of inclination, theta. And it turns out that deflection equals force times length cubed over some constant k, which later on we'll get into. The slope, theta, equals the force times the length squared. And actually, it turns out, let's give you the whole 3 times the modulus of elasticity times the moment of inertia, 2 EI. This tells you there are more intelligent factors in the universe than your average Cocker Spaniel, because 2, 2, 3, 3. It's really beautiful. Right away, your brain should start to be thinking about, wow, that's really interesting. What is cool about that? Well, for optics, sometimes you want to align a lens. You want to have something in a lens where I just do something to it very simply, and I want to have pure tilting motion. I don't want to tilt and translate. I want to have pure tilt. So if I were to mount a lens here and push on the mount for the lens with a force F, I would get tilt in the lens and a translation. I don't want that. I want to mount the lens somehow such I get pure rotation. This is what Bill needed to do for calibrating lenses. I believe it was for the SX70, which is one of the most brilliantly designed and successful cameras ever. So he looked at these relationships in his mind and said, wow, I can use the Abbe effect to cancel, this is like the reciprocity thing going on, this translation error. So all I need to do is take this angle times a length times 2/3, and I will get an Abbe offset of FL cubed over 3EI. So all Bill has to do is mount his lens back here at 2/3 L. This total length is L. And when you push on this beam with a force F, any force F, is it bends. And remember, it's not mounted to the beam, it's mounted to an arm on the beam. This arm on the beam will deflect up, and the lens will stay put, but it will tilt perfectly. So here's how you can use something you may say, man, that's a problem, to your benefit here and here, and avoid the problem, for example, in measurement. What did we just do? We took something that was a problem, a potential problem, a really cool fundamental principle to help us identify problems in machines, that we have a problem. It's a problem, it's fundamental, it's beautiful, it's just physics and it identifies problems. And what do? We turned it into an opportunity. So it's very, very, very important to always be thinking through things, that as you're designing machines, as you're applying these philosophies, and you're identifying things that, well, that's a problem. Boy, I sure am glad I know fundamental principles because I nailed that problem. Turn it around. And turn an opportunity for design either in that mechanism or somewhere else. Very, very critical. Let's have some fun with this now. Everybody knows that plastic toy blocks, for example, Legos, very, very high precision. You put them together wonderfully, and you make nice straight beams and good things, right? Well, it turns out that in order to actually manufacture them and use them, you've got to have small little gaps between things. You've got to have little spaces, because if they were exact, and due to uncertainty in manufacturing, even by 1 micron, if you designed them to be exact and they were a little bit too big, they wouldn't go together. So you leave a little bit of spaces to make this nice, straight, beautiful wall. But you can take something that's nice, perfect, straight, that's got little spaces in it, and you can bend it. So we actually, my kids and I, we used to make Lego roller coasters. It's a lot of fun. 1 over problem equals opportunity. Very, very important. When you think of a milling machine, for example, big, rigid cast iron. It actually's got little spaces everywhere in it. And this super precision machine with little spaces in everywhere, you start machining and things move a little bit, and it opens up a little bit. You normally don't care. But if you were designing a machine to make the optics that go into the wafer steppers that go to make the silicon wafers, which go into making everything electronic, that cascading of errors can build up very, very critical design rules. And the ability to model this mathematically is what enables you to actually design a machine rapidly, get it to market fast, and knowing how it performs because you have the mathematical model for it enables you to identify the uncertainties and the sensitivities and head them off at the pass. Yee-haw!